radiation from the stars. Here we have f of lambda, which is a function of lambda, the wavelength. And here shown is Planck's model for blackbody radiation. We have a lot of annoying constants here, so let's express them as one letter. Let hc equal a and kt equal b. This will be helpful later on. Problem 1 asks us to find the limit as lambda approaches 0 from the right of f of lambda. The limit as lambda approaches 0 from the right is written here, factoring out the constants 8 pi hc. The limit of the numerator as lambda approaches 0 from the right is infinity, and the limit of the denominator as lambda approaches 0 from the right is also infinity. This gives us an indeterminate form, infinity over infinity. And so this means we can apply L'Hopital's rule to our limit. So we take the derivative of the numerator with respect to lambda and the derivative of the denominator with respect to lambda, giving this expression. From here, we'll ignore any of these constants by factoring them out and dealing with them later. Note that none of them are dividing by 0. This limit gives us an indeterminate form, infinity over infinity again, so we can apply L'Hopital's rule again. Here we'll be applying L'Hopital's rule a little bit faster so we can get through this quickly. Take the derivative of the numerator and denominator with respect to lambda and independently gives us an indeterminate form, infinity over infinity again. Applying L'Hopital's rule again gives indeterminate form again. Applying L'Hopital's rule again gives us the same indeterminate form. Applying it one final time gives us a limit which evaluates to 0. And since we know none of these constants divide by 0, the constant times 0 equals 0. The answer is thus 0 watts per meter cubed. As lambda approaches 0 from the right, so too does f of lambda, which makes Planck's model better than Rayleigh-Jean's law, which goes without bound as lambda approaches 0 from the right. We know this is desirable in a model because it's empirically measured that a black body of a certain temperature emitting radiation approaches 0 as wavelength approaches 0. Approaching 0 makes Planck's model a better model for black body radiation. For problem 2, we have to use the Taylor series centered around 0 of e to the x, where x is hc over kt lambda. Expanding out, we get this expression for Planck's law, and we're going to be using those first two terms there to approximate. And we're only using the first two terms of the Maclaurin series because all subsequent terms will be very small compared to the contribution of the ones given to these first two for large lambda. So we can approximate using those two. Rewriting the expression using the first two terms of the Maclaurin series gives us this. The ones cancel, simplifying down to this. hc divided by hc will cancel. Lambda to the negative 5 times lambda gives us lambda to the negative 4. And this expression simplifies to 8 pi kt over lambda to the 4. This is exactly the same formula as Rayleigh-Jean's law, which means that for large wavelengths, the approximation of Planck's law gives the same value as Rayleigh-Jean's law. Thus, Planck's law gives approximately the same values as Rayleigh-Jean's law for large lambda. Question 3 requires us to graph Rayleigh-Jean's law, here graphed in blue, and Planck's law, here graphed in red, for given constants. Planck's law is maximum on positive values, as negative values are irrelevant here. The graph increases going towards 0 until it reaches a maximum here, and then starts to go back down to 0, going from the right. Rayleigh-Jean's law has an asymptote as lambda equals 0, so the model predicts that at energy densities of low lambda, the energy would grow without bound. For larger wavelengths, the two models are almost identical and agree on their behavior on black body emitting radiation at that wavelength, which corroborates with problem number 2. For problem number 4, we have to estimate this peak wavelength emission for this given constant of using Planck's law. Plugging it into Wolfram alpha and finding the local maximum within this range gives us lambda equals 5.08 times 10 to the negative 7 meters. Problem 5 requires us to graph Planck's model for different stars which have different temperatures. Sirius here in blue, Procyon in purple, the Sun in orange, and Betelgeuse in red. Here we've zoomed out so you can see the maximum of Sirius. As T increases, the peak shifts to lower wavelengths, so to the left, and peak wavelengths emitted. So the peak wavelength emitted is decreased. Shorter wavelengths of light are thus emitted by hotter stars. This explains why Sirius is a blue star, as it is the hottest out of the group, and thus emits the greatest amount of short wavelength light. Human eyes perceive short wavelength as blue, and Betelgeuse emits light with a longer wavelength, and is thus a red star, as human eyes perceive those long wavelengths of light as primarily red. This is shown on the visual on the electromagnetic spectrum. As T increases, the total radiation emitted, the area under the curve, increases. As heat, which temperature measures, is a measure of energy which must be radiated. On all energy must be radiated out. So it makes sense that the total energy / radiation emitted is increased as temperature is increased. Here, peak wavelength for Sirius is outlined, and peak wavelength for Betelgeuse is outlined in green for Sirius and in black for Betelgeuse. Here's the electromagnetic spectrum with lambda increasing to the right. The visible spectrum here is zoomed into. Here in green, we show the peak wavelength emission for Sirius, which is in the blue range, and the peak wavelength emission for Betelgeuse, which is in the red range, which explains their perceived color.